now that we have an idea about standard deviation and how that is used to represent a data set, then we're going to talk about normal distributions and the percentages of values or amount of data that we can expect to see within certain standard deviations. This is called the empirical rule. It's also sometimes referred to as the 68, 95, 99.7 rule. So a normal distribution are the ones that are symmetric. It has a single peak. They are often referred to as the bell curve because it just kind of looks like a bell and then opens at the bottom. At the center of the curve is the mean of your data set. We use the mu Greek symbol to represent the mean when we're working through these problems. The standard deviation is represented by sigma. That's our standard deviation or the variability. It's the spread of the data from the curve. And we can have data that's really spread out. So the example to the left, you see that the mean's in the middle. The standard deviation is a little bit larger because that bell is a little bit flatter versus the one that's a little bit higher. So you've been seeing a lot of different curves, especially as we've been going through this pandemic, as they talk about flattening the curve. This is what they're talking about when they're referring to that language. We can use normal distributions to talk about real data. So again, the pandemic is an example as we talk about, people catching the virus and then being hospitalized. Test scores are often under a normal curve. Biological measurements, height, things like that are a normal distribution. Things like probability, so tossing a coin, how many times you're going to get heads, how many times you're going to get tails, also gets measured under a normal distribution. And then IQ scores, so an average IQ I think is 100, and then you go out from there, and then you have people that would be a genius at the higher end, and you have people that are mentally handicapped would be at the lower end. So the empirical rule, again, we said is just this idea that 68% of the observations should fall within one standard deviation of the mean. So as we talk about things that are normally distributed, most of the data should be within one standard deviation of the average. 95%, most all of your data, if it's a normal distribution, will be within two standard deviations of the mean. And then almost all, 99.7% of the data should be within three standard deviations of the mean. So if we go back and think about an example such as height, you can have people that are, 2 or 3 standard deviations above, meaning they would be really tall compared to the average height, or 2 or 3 standard deviations below, meaning they're much shorter than the average height. Most of our population should be within those 3 standard deviations. We don't have a lot of people that fall in height ranges outside of those values. So again, with the normal distribution, we can think about the curve and what we're seeing. We can use the inflection point to kind of let us estimate where one standard deviation above and below. So that's, again, where the curve changes from concave up to concave down, vice versa. We looked at that when we talked about polynomial functions, but we're just thinking about the curve. Wherever that change takes place is approximately one standard deviation on either side of the mean. And I just say that because it's helpful when you start to kind of sketch these and think about visually what's happening with some of these data sets to kind of have an idea of where that value falls. If you made your foldable or if you copied this into your notebook, this is the breakdown of all of our data points. So one standard deviation above 34% of the data, one standard deviation below 34% of the data. That gives us our total of 68%. The next value, so between 1 and 2 standard deviations, either above and below, would be 13.5%. 3 standard deviations above and below, 2.35%. And then the really small percentage of 0.15% would be above 3 standard deviations. Because again, we said there's a very small percentage of a population or a data set that should be 3 standard deviations above or below if we have a normal distribution. So it's not to say that it doesn't happen, it's just saying that statistically when people are looking at data sets, they just need to have an idea of about how much of the data should be within those values. It can vary, but generally this is the rule that it's going to follow. So how do we use that? How do we use this information to answer questions and to think about statistics? So we said the distribution of adult American men's height is approximately normal. So you do have to have that phrase. They do have to tell you that the data set is approximately normal. They'll tell you the mean, 69 inches, standard deviation, 2.5 inches. So we're going to draw the curve and mark the points of inflection. So here's our normal bell curve. Again, mu means mean. Theta is your standard deviation above and below. So we always take and put the mean in the middle. So average male height, 69 inches. If we are 1 standard deviation above, we would add the 2.5. So 1 standard deviation above, you should be between 69 inches and 71.5 inches tall. 2 standard deviations would be 74 because I would add another 2.5. And then 1 more would be 76.5. So if you were taller than 76.5 inches, that means that you would be more than 3 standard deviations above the mean for average height, and you would be considered very tall. 66.5, so going the other direction, we subtract the standard deviations. So 66.5 inches would be 1 below. 64 inches tall, you're 2 standard deviations below. Most people should be within 2 standard deviations. If you are 61.5 inches tall or less, then you would be 3 standard deviations below. And again, not a lot of people are going to fall into that height category for males. If you're less than that, we would just say comparatively that you are shorter than most people as well. So this notation, you've been seeing this on some of the slides. Again, the n just tells us it's a normal distribution. The first number is the mean, so 69 inches is the mean height for American males. And then the second number, 2.5, is your standard deviation. So you can also be given your data using that notation. Your inflection points, again, are going to be at the 1 standard deviation above and below. So we would have 2 inflection points there on that graph. And again, we know that that happens at the 1 standard deviation mark. So the question would be, what percent of men are taller than 74 inches? They could also ask you for proportion, and proportion would just mean that you're going to take, rather than giving those numbers as percentages, you would give them as a decimal. So don't let that, if you see that phrasing, don't let that throw you off guard. It means the same thing. So 74 inches is 2 standard deviations above. So we want to know the percent that is taller than 74 inches. So we're looking at that part of the area under the curve. And we know from our empirical rule that we would take the 2.35 and the 0.15% in both of those bins, basically, add them together to give me 2.5%. So 2.5% of men should be taller than 74 inches. So not a lot. Between what heights do the middle 95% of men fall? So again, we know from our empirical rule, 95% should be between 2 standard deviations above and below. So we would look at those 2 values to answer that question. So the 95% of males should fall between the height of 64 and 74 inches tall. What percent of men are shorter than 66.5 inches? So again, if you have your normal distribution drawn out, so that's the first thing I always do on these problems is draw that distribution out and label. So I would find 66.5 inches. I would see how many percentages or standard deviations that I have to look at. So there's 3. So 0.015%, 2.35%, and then 13.5%. We add those together to get 16%. So 16% of men are shorter than 66.5 inches. If they asked you proportion, then you would have just said 0.16. So the most important thing for this is making sure that you memorize those percentages in between each standard deviation, and you know how much of the data should be there. And if you, again, can remember that empirical rule, that will help you with that 68, 95, and then 99.7%.